Thanks, Errol, for the introduction. Hello, everyone. Today, I would like to tell you about this project, which connects metrological bounds and quantum error correction. And this work was done jointly with Rafał Demkowicz-Dobrzański, who is at the University of Warsaw. So let's get started. What we want to do in our field in quantum information processing is we want to process quantum information in a fault-tolerant way. We want to have logical information well protected from noisy environment, which can introduce errors. But at the same time, we also want to implement logical operations, and we want to be able to implement them in an easy way. However, as we will see, there's a tension. And namely, if we can protect logical information from the environment, usually it means that logical operations are not so easy to implement. So what are the easy to implement logical operations? The easiest way to implement a logical operation would be to implement a unitary, which is a tensor product of single qubit unitaries. And those unitaries, which I will refer to as transversal gates, they do not spread errors. So if there is something bad happening in the system, if one qubit is affected by noise, say, but then if we apply a transversal gate, this error does not propagate to other qubits. And this is not a case with unitaries implemented, say, via constant depth circuits. Those errors can spread. And if the circuit becomes more deep, the errors can spread in a very detrimental way. So what we would really want to have is we would like to have a non-trivial quantum error correcting code, a code which can correct errors, which can suppress errors, which has transversal gates, which form a universal set of logical gates. And then if we encoded logical information into such a code, all what we would do is we would implement those transversal gates, and we could perform arbitrary computation. The information would be protected, and we would be very happy. Unfortunately, this is only our dream, and Eastin-Knill told us a couple of years ago that this is not possible. We cannot have a non-trivial quantum error correcting codes with transversal universal gate set. So a natural question is how we can avoid this no-go theorem. How can we do fault-tolerant computation? And also, a natural question is to ask how fundamental is Eastin-Knill theorem. And in this talk, I will be looking into the question of what happens if there is an equivalent version of Eastin-Knill theorem if we don't use exact error correction, rather we focus on approximate error correction. So here's the main result and the outline of my talk. So in this talk, we will establish a version of Eastin-Knill theorem, the approximate Eastin-Knill theorem, which is applicable in the case of approximate quantum error correction. And our version of the Eastin-Knill theorem is applicable to many relevant noise models, including the erasure and depolarizing noise models. Our proof is very simple, and our approach taken in this work is a bit unorthodox. Namely, we use quantum metrology to tell us something about quantum error correction. Normally, people use quantum error correcting codes and ideas from quantum error correction to improve metrological protocols. But we will go in the other direction. So here's what we're going to start. First, I will set the stage and tell you a bit about quantum error correction with an emphasis on approximate quantum error correction. And then I will tell you more about the approximate Eastin-Knill theorem, and I will put it in some broader context. Then I will very briefly introduce some tools needed to understand the main idea of our proof, and those tools include quantum metrological bounds. And I will finish with a sketch of our proof. So for the purpose of this talk, a quantum code is just a subspace of the Hilbert space. So what do we have? We have some logical information which we want to encode into some physical system. The encoding map E takes our logical state and encodes it into the physical Hilbert space. And throughout this talk, I will assume that the physical space admits this tensor decomposition into n subspaces. The number of subsystems n is finite, and the dimension of each and every local Hilbert space is finite. So you can think of those subsystems as, say, qubits or qubits. So now, once we have a code, we can ask a question if we can correct some errors. So given some set of errors, can we correct them if we encoded the information into some error correcting code? And here is where the Knill-Laflamme condition becomes very helpful, because it tells us that there exists a recovery operation which can undo the effect of errors on our encoding information if the following condition is satisfied. So it's a very simple condition. And I would like to emphasize that here we're talking about correcting errors exactly. So given some set of errors, which satisfy the Knill-Laflamme condition, we can undo them exactly. And also, we can, if a Knill-Laflamme condition holds for the set of errors ki, any linear combination of ki's is correctable as well. So the notion of the code, which shows up here, is the notion of the code distance. So we say that the code has distance 2t plus 1 if any error of weight at most t is correctable. So now let's switch gears and talk about approximate quantum error correction. So if we allow for negligible error in the recovery, this can lead to surprisingly better codes. So what's the setting of the problem? So we have some noise n, and then we can choose our code E and the recovery operator R. And usually what we assume is that the noise has this tensor product structure, and the noise acts independently on each subsystem. So what we want is that the encoding followed by the noise, followed by the recovery operator, this composite channel is as close to the identity channel on the logical level. And this can be quantified in terms of Beer's distance for channels. This is some distance for two channels, which uses the notion of worst case entanglement fidelity. So what Benny and Oreshkov proposed is they proposed the following definition. And so we say that a code E is epsilon correctable under noise n if there exists a recovery operator R such that the distance of the composite channel and the encoding followed by the noise followed by the recovery is epsilon close to the identity channel in terms of the Beer's distance. Okay, so that's the setting of approximate error correction. So now I would like to tell you about the approximate Eastin-Knill theorem. So first, let me remind you what Eastin and Knill told us. So they told us that there is no non-trivial quantum error correcting code with a universal set of transversal gates. So this is a theorem. We can ask, what if we remove certain assumptions of this theorem? Will it hold? So first, we can loosen the notion of transversality, and we can consider say unitaries implemented via constant depth circuits, or maybe we can consider different partitions. We can also ask what happens if we use some non-unitary operations. And for instance, this approach is used in magic state distillation. Also, we can try to avoid Eastin-Knill theorem if we use different codes. This is the method of code switching. And here the idea is that instead of having one code, we consider two codes, and in each code we have different transversal gates, but together they form a universal gate set. Also, we can consider infinite dimensional codes where the dimensionality of a local hyperspace is infinite, and this would be a way to avoid Eastin-Knill theorem as well. And lastly, we can abandon the idea of exact error correction, and we can focus on approximate quantum error correction. And this is where the approximate Eastin-Knill theorem arises. And last year at QIP, there was a talk about the approximate Eastin-Knill theorem. So this is the setting I want to focus on in the rest of the talk. So let me rephrase Eastin-Knill theorem in a slightly different way than previously stated. So we can think of their result as follows. So let's assume that we have a quantum error correcting code E with transversal universal gates. Then what the Eastin-Knill theorem says is that such a code will have a code distance of 1. So now we can try to modify the assumptions which go into that reasoning. So first, we want to consider an approximate quantum error correcting code E, and let's assume that it is epsilon correctable under some noise n, which has its tensor product structure. And remember, epsilon correctability tells us that the composite channel encoding followed by the noise followed by the recovery is approximately is close to the identity channel on the logical level. Okay, and instead of considering transversal universal gates, we can consider transversal U1 rotations. And to be more precise, what I mean here is that the code E exhibits the properties of U1 covariance and transversality. So what you should think of is the following. If I want to implement a rotation by some angle theta on the logical level, this logical rotation can be implemented on the physical level as a tensor product of local physical rotations. And in particular, if the logical rotation is generated by some generator T sub L, then the physical rotations are generated by some local generators T sub AI. So in that setting, we will not have a notion of a code distance, but what we can hope for is maybe to arrive at some lower bounds on epsilon. So basically assuming that the code is U1 covariant and has transversal implementation of those gates, will we have some lower bound on epsilon, on the quality of the code? And it turns out that this is indeed the case. And let me just make a remark in passing that U1 covariance, which I assume here, is a weaker assumption than assuming that we have a universal gate set. And the way you should think of it is that U1 covariance is like asking about rotations along the z-axis, whereas a universal gate set is asking about the rotations along the x, y, and z axis. Okay, so we're ready to state the Eastin-Knill theorem. So in its approximate version, so the theorem says that the following: let E be a U1 covariant code with transversal logical gates, and those are the rotation generated by the generator TL. If the code E is epsilon correctable under noise n, then epsilon is lower bounded by some quantity, and that quantity, what goes into that quantity, basically it's the eigenvalue spread of the generator of the logical rotations and some quantity f up, which is a bound on the quantum Fisher information of the output of any metrological protocol. So it's some quantity we can calculate. So how should you think about this theorem? Namely, there's a price to pay. So code's quality is limited. And I would like to emphasize that this bound is easy to evaluate for many relevant noise models, including the erasure and the depolarizing channel. And it will be, so here's the formula for it. And also, I would like to emphasize that this theorem can be cast in a different way. We can have a different version of it. We can say that, if our code encodes one qubit into n qubits and has a transversal universal gate set, then epsilon is lower bounded by some quantity, which depends on the dimensionality of the local Hilbert space. Okay, so now I need to tell you a bit about tools needed. So in quantum metrology, one of the most fundamental problems is a channel estimation problem. So we have some channel, which depends on the parameter phi. We can input any state into the channel. We can perform any measurement of the output of this channel. And now what we want to do is we want to find some unbiased estimator, which allows us to estimate the parameter phi. And what we want to do is we want to minimize the variance of this estimator. So here's where quantum Fisher information becomes very handy, because it allows us to bound the variance via the quantum Kramer-Rao inequality. So basically the variance is lower bounded by the reciprocal of the quantum Fisher information. And quantum Fisher information can be computed for pure states quite easily. In this expression, phi sub phi dot denotes the derivative with respect to the parameter phi. And in the special case where when we consider unitary evolution, we can recover the time energy uncertainty relation. So now let's consider that we want to estimate the parameter phi, and we can use this channel n times. So the relevant question to ask is how quantum information would scale with n. And people considered this problem a few years ago. So if one considers an uncorrelated scheme, it turns out that quantum Fisher information can scale only linearly in the number of channel uses. However, if we use some entanglement enhanced scheme, the quantum Fisher information can scale quadratically in n. So we can achieve better precision, and that scaling would be the so-called Heisenberg scaling. However, if we, in the presence of noise, it can happen that quantum Fisher information may scale only linearly in n. And we can establish some bound on how quantum Fisher information would scale. And this bound is in terms of Krauss operators, which represent the noisy parameter encoding channel. Our say unitary rotation U followed by some local noise. And if Krauss operator, if we can find a Krauss representation which satisfies certain condition, then this scaling is linear. And usually this scaling is achieved for many relevant noise models, for most relevant noise models. Okay, so those are the components. And now I can tell you a bit about the proof, or simple proof. So let me remind you what the theorem is. So we have the code, which is U1 covariant and has transversal logical rotations. And if this code is epsilon correctable under noise n, then epsilon is lower bound by some quantity. And recall that epsilon correctability was basically that the encoding followed by the noise followed by the recovery operator. This is epsilon close to the identity channel on the logical level. And U1 covariance and transversality meant that we could have pushed the logical rotation from the logical level to be a rotation on the physical level. Okay, so what's the intuition behind our theorem? The intuition is that if our code performed too well under noise n, then we would be able to construct some metrological protocol, which would be based on the encoding channel and the recovery operator. And this metrological protocol would violate quantum metrological bounds on the precision of parameter estimation. So that's the idea behind our theorem. So here's the sketch of our proof. So what I depicted here is the most generic quantum metrological protocol. So we know from metrological bounds that quantum Fisher information of the output of that protocol cannot scale. It is upper bounded by some quantity. This f up quantity, which we can estimate for many noise models. Okay, so we know that this holds for an arbitrary metrological protocol. So in particular, it would work for a protocol which is based on our code, which is based on the encoding operator and the recovery operator. So the quantum Fisher information of the output of this protocol cannot exceed our upper bound. Okay, but now we use assumptions about the covariance and transversality of this code. So we can push the unitary from the physical level to the logical level. Okay. And now this is an equivalent, middle and bottom panel are equivalent. So now we can analyze, we can compute the quantum Fisher information by analyzing what happens in the lower panel, what happens on the logical level. And what we need to use in our proof is one technical lemma, which I don't have time to go into. All what you need to know at this point is that this technical lemma allows us to relate the quantum Fisher information to the Beer's distance. And if we use some further assumptions about our code, namely that it's epsilon correctable, and we use some contractivity and unitary invariance of the Beer's distance, as well as some triangle inequality, we can lower bound it even further. And then if we combine all those inequalities together, we can find the tightest bound on epsilon for a certain m. And basically, if we plug those numbers, we recover the statement of our theorem. So I would like to make a few more comments about our theorem. So there have been previous works on the approximate Eastin-Knill theorem, which were presented last year at QIP. So compared to those works, our proof is quite concise. We have a different way to think of the approximate Eastin-Knill theorem. We use quantum metrological bounds to show this result. We arrive at similar scaling, and importantly, our proof is applicable to beyond the erasure noise or beyond simple noise models. We can, as long as we can establish quantum metrological bounds, there's nothing which limits us to one particular noise model. Also, from our theorem, we can recover as a corollary the Eastin-Knill theorem. And the proof of it is basically a one-liner. So let's consider the erasure noise, and then we know that if the code has distance d, then epsilon would scale as p to the d. On the other hand, from quantum metrological considerations, we know that this quantity would scale, written on the right hand side, that quantity would scale as p. So for sufficiently small p, the left-hand side would be smaller than the right-hand side, but this would violate our theorem. So basically, this is a proof by contradiction, which establishes the standard Eastin-Knill theorem. And the last remark I would like to make is that quantum Fisher information, if quantum Fisher information scales quadratically, then the bound we get in our theorem is trivial. And it better be trivial because it is consistent with the existence of the 3-qubit repetition code. This code can correct bit flip error, but at the same time has logical Z rotations implemented in this transversal way. Okay, so this brings me to the summary of my talk. So in my talk, I was trying to tell you a bit about tension between doing correction and implementing fault-tolerant computation in a simple way with transversal gates. And this tension is captured by the approximate Eastin-Knill theorem. And the version of the theorem we established, it is applicable to many noise models, and the bound can be quite easily computed for relevant noise models, including the erasure and the depolarizing channel. And in our proof, we followed this novel approach, namely we use quantum metrological tools to say something about quantum error correction. And with that, I would like to thank you for your attention.
Okay, Aleksander, thanks for a great talk. So there was a question, I've asked for clarification of exactly what they're asking, but I'll ask what a variant of the question that I was thinking of, which I think maybe the Slack channel is asking for. So when you say that you assume, you consider the case when the code is U1 covariant, so you have some family of rotations that are generated by one Hermitian operator, and it's transversal for all of the angles theta. You said that was weaker than the standard assumption of having a universal set of logical gates, but for universal set of logical gates, usually you just require that they're dense, right? So I can see that it's weaker because it's on a one-line segment rather than all of, let's say, SU2. But like, do you think that there's anything hidden in the difference between approximate and like do you think the result could be extended to also cover approximately covariance? Is that distinction important?
So as far as I understand, what Feist and collaborators showed in their paper in the appendix is basically when that those two notions are equivalent. So so there may not necessarily be a distinction there. And
okay, brilliant. And so my additional moderator, Mike Vasma, was also going to ask a question.
Yep. Hi, thanks for the great talk, Alex. So we have another question in the Slack about your epsilon. So the question is, do you have an upper bound on it? Or to put it differently, how good is your bound?
Yes, so so in our so this is a good question. So one can ask whether this bound is saturated and what codes can achieve if there are codes which saturate this bound. And with our approach, we don't necessarily know whether those codes exist. But other works, Feist et al. And Woods and Alhambra, they were thinking about codes, and in certain cases, those bounds can be saturated. But we haven't thought of codes which saturate the bounds.
Okay, and time for one quick more question. So I've got a question which is, does the technique extend also to approximately covariant exact codes? So maybe this is the question that I was getting mixed up with the one that I actually asked. I've asked for a clarification what they mean, and they said that can the encoder be exchanged with the logical gate up to a small error? So can you swap the role of the encoder and where the gate is going in?
So let me make one remark where this notion of covariance is quite important. So in our reasoning, we talk about quantum Fisher information, and quantum Fisher information is is a quantity which for which you have to be able to compute like derivatives. So so that's where it's important that you have this covariance that you can take a derivative with respect to the parameter you're investigating. So if you start, so it's all good, and I think it's good to ask about what happens in those discrete cases. However, the analysis becomes more difficult.
Okay, thank you, Aleksander. So time's up now, so we're going to move to the next speaker. Let's all virtually thank Aleksander. And if you have any further questions, you can ask him in the round table, which will start at the end of the whole session. Okay, thank you, Alex.